Hey everybody, welcome back to the channel. Today we're going to talk about major and minor resonance contributors and how to distinguish between the two. Last time we kind of talked about resonance, and to review, resonance refers to the phenomenon where a molecule or an ion can be represented by two or more valid Lewis structures. And structures, called resonance structures, depict various possible distributions of electrons within the molecule. And I think I touched on this briefly, but the actual structure of the molecule is a hybrid of all resonance structures. But in this case, there are some that show up more than others. And that's where major and minor resonance contributors come in. So to kind of start, I want to start with an analogy on this. Let's say you're building a Lego skyscraper and you have a pile of Legos and you just decide, you know what, I'm not following the instructions today. And you just start putting them together and, they're Legos and it's a straight building ish, but it's kind of disjointed and it's like, yeah, I guess you could call it a skyscraper, but it's not very stable, kind of all over the place. Now, let's say you actually decided to follow the instructions and you make one that looks like this. Like, yeah, that's a skyscraper. Cool. It's actually looks like it's supposed to be built. And in essence, you could say these are both skyscrapers, but obviously the one on the right is better than the one on the left. And this is where major and minor comes in. A minor resonance contributor could be the one on the left, whereas the major one could be the one on the right. So, with all that said, great. I've told you about Lego skyscrapers, but let's take a look at how to actually determine this in organic chemistry. So, how do we decide which resonance structures are major and minor contributors? In this video, we're going to look at 4 rules that you can kind of follow to figure this out, and we're going to go from most important to least important. So the first rule we have to follow is honoring the octet rule and following the honk rule, which is something that we went over in a previous video. If you need a review on that, go ahead, but I'll try to summarize it pretty simply. That's kind of following the idea that hydrogen likes one bond, oxygen likes two bonds attached, nitrogen likes three bonds, and carbon likes four bonds. And when we look at the total electrons on an atom, we want it to equal 8. As you remember, other than like hydrogen that only wants like the one bond like that, oxygen's going to have two bonds. So it'll be 2, 4, 6, 8. Nitrogen will have three bonds, but it'll be 2, 4, 6, 8 electrons, and carbon will have four. So 2, 4, 6, 8 electrons. We have to follow this rule. This is by far the most important rule when looking at resonance contributors. The second rule that we want to follow is minimizing formal charges. So the major contributor should have the fewest formal charges because structures with excessive or unnecessary charges are less stable and therefore they're less significant to the overall resonance structure. The next rule that we want to follow, the third one, is charge placement. And what does that mean? Well, it means that negative charges should be placed on the most electronegative atoms. And as a reminder, electronegativity increases on the periodic table as you go up and right, with fluorine being the most electronegative element. How can we apply this? So let's take a look at oxygen versus nitrogen. If we have something that looks like this, where oxygen has a negative formal charge, and then we look at something like nitrogen that has a negative formal charge, we want the oxygen that has a negative formal charge over the nitrogen because oxygen is more electronegative than nitrogen. Because oxygen is more electronegative than nitrogen, it's able to stabilize and hold that negative charge better than the nitrogen is. So conversely, we can also look at this through the means of positive charges. We want the elements with the lower electronegativity to have the positive charge on it if that's applicable. So again, we'll look at oxygen and nitrogen. And let's say this oxygen has a positive formal charge, and so does this nitrogen. We want this nitrogen here to have the positive formal charge instead because it is less electronegative. Because it's less electronegative, the nitrogen is better able to accommodate for the deficiency of electrons. The final rule that we want to look at is minimizing charge separation. And The major contributor should have as little charge separation as possible because large separations of positive and negative charges decrease stability and make the structure less favorable. So, charge separation increases the potential energy of a molecule because opposite charges naturally attract. This is a given. For example, if a resonance structure has a positive charge on one atom and a negative charge far away on another, this results in an energetically less favorable structure. By minimizing this separation, so by keeping the charges closer together or neutralizing them, this will reduce the energy and make the structure more stable overall. So now that we have a little bit of a grasp on 4 rules that we need to take a look at for major and minor resonance contribution, let's do an example problem. Here is acetic acid, or CH3COOH. Pause the video if you need to, but I want you to try and figure out which one's the major contributor, which one's the minor, and then which one's somewhere in between. Pause the video, take as much time as you need. Okay, let's take a look at which one's the major one first. So given what we have here, immediately we can see that this one has no charges at all. And it happens to also abide by the octet rule. So we can say that this first one is the major resonance contributor. It follows the octet rule, there's no charges anywhere. It's by far the best of these 3. Let's take a look at the second 2. At first glance, it may seem that this one this in the middle is the second contributor because there's a minimal charge separation. The negative on this oxygen is right next to the positive on this carbon, whereas over here we have the negative on this oxygen, and over 2 elements we have the other positive on this oxygen. So we may want to say that this is number 2 and this is number 3. However, that's not the case here because remember the first and most important rule, and that is the octet rule. Now let's go ahead and take a look at the second and third resonance structures. Off first glance, it may be easy to say that this middle one is the second contributing and the third one is the least contributing based on the charge separation, which is a valid point. There's a negative on this oxygen right next door to the positive on the carbon, whereas over here there's a negative on the oxygen, but 2 atoms over, there's the positive on the oxygen. Even though the charge separation take is valid here, we have to understand the number 1 and most important rule. If you look closely, the positive on this carbon right here completely violates the octet rule. There is only 6 electrons on this carbon, which is by far the biggest violation of resonance. We need 8 electrons on carbon. We can have a positive charge, which is okay, but we need another pair right here to make this valid. So this is actually the number 3 contributor, the least, and this is the number 2 resonance contributor, so it's the middle, somewhere between 1 and 3. So when you're doing this, really the biggest key is to remember the order of importance and base your decisions off of that. There may be some charge separation, but if one of the structures violates the octet rule, we have to take that in consideration over anything regarding charge separation. Hopefully all this makes sense. Just remember your rules from most to least important, with the number 1 absolute most important rule being the octet rule. And taking all those rules into consideration, you should be able to navigate this concept effectively. As always, please like and subscribe. It really helps me out, and I will see you in the next video.